Complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born like this from the death of a star, its diameter is 50 kilometers at most. But one can find black holes of truly monstrous proportions, over 10 billion kilometers in diameter. Andrea Ghez is an expert on this invisible phenomenon of the black hole. It was when she saw the Apollo moon landing on TV that her interest in space was awakened.
My biggest objective in life when I was very young was to become a ballerina. So I think I see things spinning in space now as opposed to myself. But yeah, your path the path was unclear. And today I view doing astronomy and studying the black hole as putting together one big puzzle.
Donald Lyndon Bell predicted that a supermassive black hole lurks at the heart of every galaxy. Andrea Ghez tried to find such a black hole in our own Milky Way galaxy.
Or actually, the first thing that we're trying to do is watch how stars move. That's the key to finding that there's a black hole. And the way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Ghez followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Ghez used one of the observatories on this summit, the Keck Observatory. The Keck has 2 of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Gelessen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours. So we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star which people were very excited about in the earliest days was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is 4 million times the mass of the Sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered as natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度を見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いますけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and congratulate you on your great discovery." The letter came from England. The sender? None other than Donald Lyndon Bell, who had predicted the existence of supermassive black holes.
I was very happy because I didn't feel that I absolutely knew. I thought it was likely, and I thought it was more and more likely.
A black hole equivalent to 39 million solar masses was sucking in huge volumes of gas with its tremendous gravitational force. The dark object in the center of this artist's conception is a black hole. Its diameter is awesome, as if 160 of our suns were lined up in a row. It is now thought that almost all galaxies have these supermassive black holes at their center. The most advanced observational instruments are detecting ever larger black holes. Situated outside Earth's atmosphere, the Hubble Space Telescope can see space objects with great clarity. Hubble took aim at NGC 7052, a galaxy located 37 million light-years away. The image it captured was that of a huge disk, comprised of gases and stars. In its center, there ought to be a supermassive black hole.
When we got this image, I was just super excited, because it was such beautiful, rich detail that I really knew right when I saw this that we were going to be able to get, excellent spectra and really be able to determine whether this galaxy has a black hole and how massive it is. So I was very, very excited.
The galaxy was indeed harboring a supermassive black hole. A black hole equivalent to 300 million solar masses. That's more than 70 times larger than the one at the center of our own Milky Way galaxy. A black hole with a diameter of 1,200 of our suns lined up in a row. And Hubble has spotted an even larger one, an ultramassive black hole. This one is in M87. 59 million light-years away. Scientists had long been puzzled by a band of white light there. When Hubble was trained on the galaxy's core, the band of white light was revealed to be a gigantic jet of gases. As the gases are sucked violently into the black hole, a portion of them are ejected in the form of this jet. The mass of the black hole at the base of this jet has been calculated to be 6.4 billion solar masses. That's 10 million times greater than the supermassive black hole at the center of our Milky Way galaxy. In size, its diameter is equal to 25,000 of our suns lined up in a row. Then, in 2011, the largest black hole in history was discovered. In the galactic nucleus of NGC 4889, there's an unimaginably monstrous black hole, with a mass equivalent to 9.7 billion times that of our sun. What scientists are most eager to elucidate now is the process by which these black holes become so large. They may start with the death of a star, but how do they then grow to billions of times their original size? Trinity College at the University of Cambridge. Isaac Newton, who formulated the universal law of gravitation, conducted research here. Martin Rees has served as Master of Trinity College. Rees has conducted research on supermassive black holes together with Lyndon Bell. The impetus for his research was the discovery of galaxies whose high-energy cores were emitting powerful radio waves.
Well, there were various alternative theories about what might be happening in the centers of the galaxies, which are putting out a concentrated high source of power. And these ideas included a very dense cluster of stars, a very massive star, a binary supermassive object, etc. And I realized that if you followed forward the likely evolution of any of these objects, they would all have no alternative to becoming a big black hole.
So any object emitting sufficiently high amounts of energy will inevitably become a supermassive black hole. How then are supermassive black holes born? The Rees diagram, as it was called, charted the possible routes.
If you're going to be at that, you need to have...
In the 30 years since the Rees diagram was published, there has been a succession of discoveries of supermassive black holes. At the same time, the study of their birth has also been progressing. One scenario suggested by Rees was the consolidation of several smaller black holes. At the end of their lives, stars explode, forming relatively small black holes. Hundreds of millions of them may cluster together, merging into one supermassive black hole. This is NASA's space-based Chandra X-ray Observatory. Chandra has been examining a region where black hole consolidation is thought to be taking place. Galaxy NGC 6240 is located 400 million light-years from Earth. Actually, two galaxies are colliding there. As Chandra examines their galactic cores, two bluish-white spots appear. They are both massive black holes, one at the center of each galaxy.
This blue region here is a blow-up of the center, and you can see there are two little sources there, one brighter and one a bit fainter. But each of those, when we look at the spectrum, shows a very characteristic sign that this is just emission from a supermassive black hole in each case, which has never been seen before until we had the beautiful Chandra image and could separate the two.
Two black holes in close proximity to each other, but they cannot soon merge. Rather like the Earth and the Moon in their perpetual dance, the two black holes orbit about each other without colliding. So what about Rees's concept of black holes merging to form a supermassive black hole? Masayuki Umemura uses a supercomputer to create simulations of black hole mergers. Here, he simulates the behaviors of 10 black holes of equivalent mass. The first consolidation happens far sooner than expected. It takes only 50 million years. The process repeats. Within about 500 million years, 5 black holes have merged into one.
もともと銀河が持っていたブラックホールが、大きな銀河に取り込まれたときにブラックホールごと、中に取り込まれるわけですね。そうすると2つではなくて、例えば大きな銀河の中に10個のブラックホールがあるというような状況が最初に起こった可能性が高いということをまず想定しました。
Let's look at our actual universe. There are galactic collisions and mergers all over the place. And when galaxies merge, the thinking is that their black holes merge too. Wherever galaxies cluster, there's bound to be a cluster of black holes. That means a process of consolidation of black holes. This conforms to actual observations of our universe. A second Reese diagram scenario has a seed black hole becoming supermassive by swallowing up gases and stars. In that scenario, the monster is born by gulping down an unbelievable quantity of gases, equivalent to hundreds of millions of our sun. The gases are sucked in with so much force that the friction produces incredible heat. That violent process emits intense light and X radiation and blows away surrounding gases. The result is that there are no more gases to feed on, and the black hole ceases to grow. But how is it that such a huge quantity of gases could be sucked in the first place? Gases that are being sucked in, blowing away other gases. Ken Osuga studies this contradiction. He has found a particular mechanism within black holes by which they can continue to draw in vast amounts of gases. He's prepared a simulation of one scenario for how supermassive black holes may be created. As a black hole sucks in gases, it generates magnetic field lines, which penetrate the surrounding gas disk like hoops. Thus embedded, they are then distorted by the swirl of the disk. As the disk swirls, the magnetic field lines are caught in a spiral vortex, twisted and coiled like a spring. This is a plasma jet. A portion of the disk's gases, charged with energy such as light, shoots out in opposite directions perpendicular to the disk. Any remaining gases are sucked into the black hole, which grows supermassive.
私たちの研究の結果はですね、光の力が非常に強くなったとしても、ジェットは噴出するけども、ガス円盤からガスは変わらず吸い込まれ続けるということを明らかにしました。これによってですね、ブラックホールは大量のガスを吸い込むことができますので、巨大ブラックホールに成長するのに一役買うということを証明することができました。
Hubble has captured this actual image of an intense jet erupting from the center of a galaxy. The gas-guzzling scenario for supermassive black hole creation, as outlined in the Reese diagram, thus seems persuasive. Martin Reese developed several theories of supermassive black hole formation. One was by the continuing consumption of gases. Another was by the consolidation of smaller black holes. But the Reese diagram indicated a third possibility as well. Under this third scenario, just after the creation of the universe, large clouds of gas condensed into supermassive black holes directly, without first becoming stars at all. Recently, evidence for this third scenario has also come to light. By combining information from the Chandra X-ray and Hubble space telescopes, Priya Natarajan hunts for supermassive black holes created at the inception of the universe. These far-off galaxies were photographed by Hubble. Among those circled on the screen are some that are 12 billion light-years away. They are small galaxies, born immediately after the universe itself. Some 200 of them have been identified. Here's one as perceived by Chandra. And it already has a supermassive black hole in it. Natarajan was surprised to discover that almost all 200 of them had supermassive black holes in them. If so many supermassive black holes were already present immediately after the creation of the universe, then that lends powerful support to the third scenario in the Reese diagram.
So just as we think that a gas cloud that is collapsing could make the first star reasonably easily, the conditions that you need for making a black hole seed directly without forming a star, instead of forming a star, also exist in the early universe.
Efforts are also underway to confirm the third Reese diagram scenario computationally.
I think it is the first time that there is a model showing that it is possible to produce a precursor of a big black hole in the form of this supermassive cloud.
This is a giant gas cloud, 100 light years in diameter. 70,000 years after it formed into a gas cloud, its gases were compressed into a disk 1 light year across. The gas disk was equivalent in mass to 100,000 of our suns. It then condensed further, compressed by its own weight, giving rise to a supermassive black hole. So the third scenario in the Reese diagram, going directly from gas cloud to black hole, is a real possibility. Studies of the origins of these supermassive black holes are ongoing. The latest research reveals that the supermassive black holes do not simply grow fat, consuming everything nearby. Surprisingly, they exert a huge constructive effect on the space around them. What these remarkable monsters call home is a galaxy's core. More specifically, it's inside the concentration of stars called the bulge. The shape and size of the bulge varies with each galaxy. John Cormandy has investigated the relationship between the mass of a bulge and of its supermassive black hole. The first galaxy he observed was Andromeda. The supermassive black hole here is equivalent to 150 million solar masses. The bulge is approximately 1,000 times greater in mass. Next, he looked at the Sombrero galaxy. The black hole here is 1 billion solar masses. The mass of the bulge is approximately 1,000 times that. Plotted on a graph coordinating the masses of the bulges with those of the black holes, the galaxies form a nearly straight line. In most galaxies, the black hole to bulge ratio of masses is 1 to 1,000. This strong relationship between the mass of supermassive black holes and their galaxies' bulges surprised many scientists.
We know that when gas densities get very big, you get a burst of new stars being formed. And so at the same time when this burst of stars is making the bulge, the rest of the gas is being fed to the black hole and making the black hole bigger. So you get lots of new stars, and you get higher mass black hole, and the two correlate.
A galaxy comprises hundreds of billions of stars. It turns out that at the galactic cores, the black holes and the bulges have a deep interrelationship. A giant bulge will correlate with a giant black hole, a small bulge with a small black hole. This strange law of outer space may mean that galaxies and black holes evolve together. Andrea Ghez discovered the supermassive black hole at the center of our own Milky Way galaxy. She also found evidence that it performs an astonishing function within the galaxy's bulge.
We've had one surprise after another in our study of the center of the galaxy. What we see is that they're very massive stars, which tells us that they're very young stars. And the last thing you expect near a black hole is to find a very young star, because black holes are very inhospitable to star formation. They should just tear apart any cloud that might eventually become a star. So you really don't expect to see young stars, baby stars near a black hole. And yet all the stars that told us that there's a black hole are the ones we predicted shouldn't be there. So it's one mystery after another.
Near the supermassive black hole at the center of the Milky Way, Ghez found many baby stars. This suggests something astounding, that new stars may be emerging from the gases that originally accumulate around a black hole. The effect black holes have on surrounding space is not limited to the birthing of stars. A project spearheaded by NASA called Tanami is endeavoring to capture distant galaxies. Tanami involves the participation of radio telescopes in a dozen locations in the southern hemisphere, chiefly in Australia, but also in Chile, South Africa, and the South Pole. One of its targets is a galaxy located 14 million light-years from Earth, Sagittarius A. This is the image they obtained, a clear view of a plasma jet violently shooting out from an invisible black hole. The jet bursts out at 30% of the speed of light. Analysis of this jet turned up something quite unexpected. The jet shooting out of the black hole even escapes the galaxy itself. Its plume expands for a distance of 1 million light-years. So the black hole doesn't just guzzle down gases, it sends out the stuff that stars are made of, far beyond its own galaxy. The role of the supermassive black holes in the universe is still largely mysterious, but scientists are learning more and more.
Cosmos looks the same from Britain and from Japan. Indeed, the night sky is the same to all of us and has been the same to all our ancestors throughout human history. It's the one common feature of all humanity. They've all looked up at the night sky and wondered at it and interpreted it in their own way. It's a wonderful story where we found all these extraordinary objects in the universe, and we can understand these vast cosmic horizons in a way that our ancestors could only have dreamed of. So it's a wonderful story.
Supermassive black holes, monsters in the galactic cores. They may gobble up everything around them, but they also give birth to stars and send out energy-rich materials into the universe. Some came into being at the same time as their galaxies and grew along with them. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんですよ。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度に見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and
4 million times the mass of the sun."
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered this natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. Shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star, which people were very excited about in the earliest days, was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is...
The way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Guess followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light-years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Gez used one of the observatories on this summit, the Keck Observatory. The Keck has two of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Gillesen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours, so we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine. The black hole is a bizarre space object, defined by the absence of everything except gravitational force. How do scientists wrap their minds around it? It's complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born,
the universe has long captivated us with its immense scales of distance and time. How far out does it stretch? Where does it end? And what lies beyond the star fields and the streams of galaxies that extend as far as telescopes can see? These questions are beginning to yield to a series of extraordinary new lines of investigation and to technologies that are letting us peer not only into the most distant realms of the cosmos, but at the behavior of matter and energy on the smallest of scales. Remarkably, our growing understanding of this kingdom of the ultra-tiny inside the nuclei of atoms is now enabling us to glimpse the answer to the ancient question: how large is the universe? In ancient times, most observers saw the stars as a sphere surrounding the Earth and as the home of deities. The Greeks were the first to see celestial events as phenomena, subject to human investigation, rather than the fickle whims of the gods. One philosopher and sky watcher named Anaxagoras suggested that meteors are made of materials found on Earth, and therefore might have even come from the Earth. Those early astronomers built the foundations of modern science. But they would be shocked to see the discoveries being made by their counterparts today. The stars and planets that once harbored the gods are now seen as infinitesimal parts of a vast scaffolding of matter and energy that extends far out into space. Just how far began to emerge in the 1920s. Working at the huge new 100-inch Hooker telescope on California's Mount Wilson, astronomer Edwin Hubble, along with an assistant named Milt Humason, analyzed the light of fuzzy patches of sky, known then as nebulae. They showed that these were actually distant galaxies located far beyond our own. Hubble and Humason discovered that most of them are moving away from us. The farther out they looked, the faster these objects are receding. This fact, now known as Hubble's law, suggests that there must have been a time when the matter in all these galaxies was together in one place. Everything that astronomers saw in their increasingly large telescopes would have dated back to a singular beginning, now called the Big Bang. That the universe could expand had been predicted back in 1917 by Albert Einstein. Except that Einstein himself didn't believe it until he saw Hubble and Humason's evidence. Einstein's general theory of relativity suggested that galaxies could be moving apart because space itself is expanding. So when a photon gets blasted out from a distant star, it moves through a cosmic landscape that is getting larger and larger, increasing the distance it must travel to reach us. So how large the cosmos has gotten since the Big Bang depends on how long it's been growing, in addition to its expansion rate. Recent precision measurements gathered by the Hubble Space Telescope and other instruments have brought a consensus that the universe dates back 13.7 billion years. In that time, a beam of light would have traveled 13.7 light years, or about 1.3 quadrillion kilometers. But taking into account the expansion of the universe, the most distant galaxies discovered by the Hubble Space Telescope are actually 46 billion light-years away from us in each direction, and almost 92 billion light-years from each other. So, is that the size of the universe? It's not, according to a dramatic new theory that describes the origins of the cosmos. It holds that our 92 billion light-year patch is a mere speck within the universe as a whole. The theory is based on the discovery that energy is constantly welling up from the vacuum of space in the form of particles of opposite charge, matter and antimatter. Back in the 1980s, the physicist Alan Guth proposed that energy fields embedded in the vacuum of space had suddenly tipped into a higher energy state, causing space and time to literally inflate. The universe went from atomic size to cosmological size within an infinitesimally short time. As a result, according to Guth's calculation, the universe as a whole would have grown to some 10 billion trillion times the size of the observable universe. That's a 10 followed by 24 zeros. Put another way, the whole universe is to the observable universe, as the observable universe is to an atom. The incredible fury of cosmic inflation helps explain the immense size and smoothness of the universe. But to succeed, the theory must also account for how the universe produced what we see around us. All those stars and galaxies and clusters of galaxies, and ultimately, us. Scientists are now attempting to piece together the chain of events that launched our universe in its earliest moments by generating what you might call a little bang. At the Brookhaven National Lab in New York State, they are blasting gold atoms in opposite directions down tunnels almost 2.5 miles long. When these atoms reach velocities just short of the speed of light, they are sent into a violent collision. A fireball erupts, reaching a temperature exceeding 2 trillion degrees centigrade. As far as we know, the last time anything in our universe was that hot was about 1/1,000,000th of a second after its birth. What interests the scientists is the splatter of subatomic particles, a superhot soup of quarks and gluons that theory says gave rise to matter as we know it. In initial tests, this quark-gluon plasma has shown a crucial property: extremely low viscosity or resistance to flow. Scientists call it a perfect liquid. To grasp its importance, we go back to those primordial energy fields that the theory says spawned the Big Bang. The thinking is that those fields contain tiny fluctuations that were blown up to huge size during inflation. In the ultra-dense quark-gluon mix, these fluctuations generated pressure waves, or ripples. As the universe evolved, these ripples gave rise to variations in the density of matter. Amazingly, the imprint of those primordial ripples is out there today, in a faint signal discovered accidentally back in the 1960s. Working for the Bell Telephone Company, physicists Arno Penzias and Robert Wilson had built a giant horn-shaped antenna. But wherever they pointed, the contraption picked up excessive noise in the microwave portion of the electromagnetic spectrum. That noise turned out to match a prediction made years earlier, that in the wake of the Big Bang, the universe was filled with a cloud of extremely hot gas that scattered all light. As the universe cooled, the cloud dissipated. Light then shone through. Over time, the spectral signature of this light would have shifted as the universe expanded and cooled to what Penzias and Wilson detected. What they'd heard was the echo of the Big Bang. This image shows the smooth contours of the light recorded by the Bell team. Scientists would have to look closer to find the imprint of cosmic inflation. The Space Shuttle Discovery lifted the Hubble Space Telescope into orbit on April 24, 1990, in one of the most important scientific milestones of our time. Another launch, arguably just as important, took place 5 months earlier. The Cosmic Observation Background Explorer, COBE for short, was sent up to take a harder look at the microwave radiation discovered by Penzias and Wilson. The results came out 2.5 years later. The light of the early universe contained a pattern of hot and cold spots. In this image was nothing less than the origin of all we see around us today, smooth on a large scale, but with significant clumps, from which gravity would form gas clouds, then stars, and galaxies. With this cosmic template in hand, astronomers set out to discover how the patterns and dimensions of the universe evolved over time. In an age of computer-controlled telescopes and automated observing, astronomers could now launch huge international collaborations with the goal of mapping a large fraction of the universe in 3 dimensions. At Apache Point in New Mexico, the Sloan Digital Sky Survey set the standard for mass production astronomy. A series of steel plates are drilled with holes that exactly match the location of galaxies in the night sky. After plugging fiber optic sensors into the holes, the plates capture the light of hundreds of galaxies per night. From that light, the astronomers calculate their distances from Earth. Another survey is named the 2-micron All-Sky Survey, or 2MASS, after the frequency of infrared light its detectors are tuned to capture. In this image, the 2MASS data covers a region 60 million light-years across. The local group of galaxies, including the Milky Way, are in the center. This is our intergalactic neighborhood. Jump further out to a region about 200 million light-years across. Our location is linked to the densely packed Virgo supercluster, the nearest intergalactic city. You can see the full breadth of our local region of the universe. Galaxies line up in walls and arcs. Beyond them are sparsely populated voids, the rural cosmic countryside. Moving out with the data, this region is over 650 million light-years across. Then almost 2 billion. 3.2 billion. And finally, out to a region 6.5 billion light-years from end to end, the cosmic continent. In the middle of it all, our galaxy, so immense from our earthly perspective, is less than a speck. The 2MASS study, the Sloan Digital Sky Survey, and the 2-degree field in Australia have extended our maps to a quarter of the way back to the beginning of the universe. They have laid out a grand cosmic roadmap. COBE's successor, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched to scan the early universe for the fine-scale origins of this cosmic atlas. WMAP traveled beyond any interference from Earth to a position balanced between the Earth and the Sun. There, for 2 years, its detectors took in the pristine light of deep space. This is what WMAP saw. Tiny-scale structures that inflation would have laid out at the very birth of the cosmos. And a pattern consistent with the filaments and voids that had evolved in the universe at large. Scientists are poring over the WMAP data for clues to the true dimensions of the universe. One group, for example, looked for repeating patterns that could be evidence of pressure waves that ricocheted through the hot gas of early times. They saw none, which implies that the universe had grown so large during inflation that such waves could not cross it. Then they did the math and reported that the entire universe must have a minimum diameter of 78 billion light-years. So what is its maximum size? And what's beyond that? We will never know for sure what lies beyond our visual horizon, but astronomers are turning up some surprising hints in the universe they can see. To ancient observers, the universe was made of 5 classical elements: Earth, water, air, fire, and a 5th, quintessence, or space. Aristotle believed the stars, unchanging and incorruptible, were made of this 5th element. Today, we are finding that space, in fact, has a character of its own. Astronomers have calculated the gravitational pull needed to bind stars as they orbit a galaxy, or galaxies as they orbit a cluster of galaxies. They have found that there is simply nowhere near enough visible matter there to hold these structures together. The missing ingredient, its identity still unknown, they call dark matter. In supercomputer simulations of cosmic evolution, dark matter is added in to supply the gravitational tug needed to form the web pattern of filaments and walls, voids and dense clusters we see in the universe at large. But something else appears to be happening on these large scales. Astronomers have been making refined measurements of the cosmic expansion rate. They wanted to know if gravity was slowing down the pace at which the universe is growing. The markers they used, type 1A supernovae, are thought to burn at uniform intensities throughout the universe. By measuring changes in the brightness of these so-called standard candles at various distances, the researchers can spot changes in the cosmic expansion rate. To their surprise, the data showed that the universe as a whole is not only expanding, it's actually accelerating outward. The culprit is thought to be energy welling up from the vacuum of space, similar to what occurred in the early moments of the Big Bang, causing cosmic inflation. By emerging in minute quantities everywhere, it is pushing space outward across the whole universe. Over time, this so-called dark energy has grown to an astonishing 3/4 of all the matter and energy in the universe. With data like this pointing to an underlying dynamic within our universe, some scientists are thinking of the cosmos in far broader terms than ever before. There is a version of inflationary theory, for example, that suggests we live in one of many universes that may coexist side by side, but do not touch one another. Like bubbles, they are continually rising up and expanding across the oceans of infinity. Just 500 years ago, in Galileo's time, many people looked out into space and saw a universe of lights centered on the Earth. The invention of a telescope revealed stars far from our planet. Then galaxies, clusters of galaxies, and beyond them, vast walls and filaments of matter. Newer ideas about the size of the universe amount to a quantum leap in our sense of scale, by extending these structures far, far beyond our horizon. Do these discoveries push us, on our tiny, out-of-the-way planet, into a smaller and smaller corner of creation? Or does our ability to comprehend and imagine the far limits of time and space somehow expand our importance in the grand scheme of things? In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. And it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out. Communication streams were cut. Airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives, our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
Three, two, 1, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood. The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun. If we want to understand the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space probes scan and study the sun in ways we never imagined, even 30 years ago. By studying the sun from the vantage of space, we can see it in a whole new light, using different light wavelengths, including X-ray and extreme ultraviolet. We can peel back its layers and begin to understand how and why the sun acts the way it does.
The different wavelengths mean different temperatures, and different structures are more visible in different wavelengths than in others.
Our robotic space probes never stop watching the sun. With their help, scientists are working out the big questions about our star, and we already know a lot. The sun is one of over 200 billion stars in our Milky Way galaxy, but it is our closest at 93 million miles away from Earth, almost the same distance as 4,000 trips around the globe. And despite that distance, its light only takes 8 minutes to reach Earth. It is only 4.5 billion years into its nearly 10 to 11 billion year lifespan. And though technically a medium-sized star called a dwarf, it is enormous, 900,000 miles across, and if hollowed out, 1.3 million Earth-sized planets could fit inside. The sun accounts for 99.8% of the mass in the solar system, and it weighs 300,000 times more than the Earth. It is made up almost entirely of a superheated form of electrified and magnetized gas called plasma. The sun packs enough gravitational pull to keep the planets from spinning off into space. And as Copernicus first suggested, it rules the center of our solar system with a gravitational iron fist.
Copernicus's model, in which he placed the sun in the middle of the solar system with all the planets going around it, instead of everything going around the Earth, was a giant paradigm shift. It meant that the sun is the most important thing in the solar system. It meant that we really should understand the sun.
Our sun, like all other stars in the universe, is made from the dust of stars that lived and died over billions of years, going all the way back to the Big Bang.
So our sun and our solar system is really the debris from many generations of stars.
The sun we see every day is the solar system's source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and is the engine that drives it all.
Inside the sun's core, the process of fusion is occurring, and that fusion process is giving off light and particles.
Every second the sun shines, it releases the same amount of energy as 1 million H-bombs. The sun's light is made of particles called photons, born in the core, then propelled by convection currents through the radiative and convective zones of the sun. Eventually, they reach the volatile outer layers of our nearest star.
The sun's outer parts consist of 3 regions. There's the photosphere, or surface of the sun, and it's not really a hard surface like that of the Earth. The sun is gaseous throughout. And the temperature of the photosphere is around 10,000 degrees Fahrenheit.
Above the thin layer of the photosphere is another thin layer called the chromosphere. And the chromosphere is slightly hotter than the photosphere, which is counterintuitive because you would think that as you go away from the source of all the energy and heat, the core, that temperature would drop. But in fact, the temperature rises from the photosphere to the chromosphere. And it gets even hotter as you rise to the third layer of the atmosphere called the corona.
And then beyond the chromosphere is a large, tenuous, extended region, the corona, which is millions of degrees.
The sun produces a continuous outward flow of energy called the solar wind. Constantly blowing, it carries energy out into the solar system, extending our sun's reach 9.3 trillion miles, well beyond Pluto.
The space in between the planets and the space in the entire solar system is not an empty void, but it's full of these particles and it's full of these rays of light.
While the solar wind blows away from the sun, its gravity holds and pulls everything in. Take comets. All comets orbit the sun and can get pulled directly into the line of fire. Recently, scientists witnessed one of the sun's most dramatic outbursts, a coronal mass ejection, ripping the tail off a comet.
When it hit the comet, the tail was cut off like you took a knife, and the tail drifted away, and then it took a little more time for the comet to generate more gas and plasma and dust and create a tail. It tells us about how the solar wind moves in the solar system and how it can affect things.
The sun affects everything it touches, even us. To learn just how much, scientists sometimes rely on a remarkable cosmic coincidence. The lethal output of the sun has made studying it almost as difficult as understanding it. But scientists can get a good look at our nearest star thanks to a cosmic coincidence. A total eclipse of the sun.
A total solar eclipse occurs when, from our perspective, the moon is exactly aligned with the sun and blocks its photosphere. It's a glorious sight.
The solar eclipse is the most wonderful thing to see. It grows really dark by factors of thousands within seconds. And as it does become so dark, you can look up in the sky, you see the dark shadow coming from one direction, sweeping at you. It's really coming at thousands of miles an hour. So it's very impressive to see.
Humankind has marveled at the mysteries of the eclipse for millennia. Scientists have used it as an opportunity to see the sun's outer atmosphere, the enigmatic corona. One of the hottest regions of the sun, energy from the corona radiates out to the edge of the solar system.
The entire solar system actually sits in this outer corona of the sun. So this atmosphere of the sun is bathing all the planets.
The engineers who built the Solar and Heliospheric Observatory, or SOHO, installed an artificial eclipse into the space probe. Called a coronagraph, it does the same thing as a natural eclipse, blocking out the blinding rays of the sun, so scientists can try and answer an old question.
How does the solar corona get so hot? After all, the everyday surface of the sun, the photosphere, is only around 10,000 or a little more Fahrenheit. And the corona, on the other hand, is millions of degrees hot. If you go away from a stove, you know it gets cooler, but if you go away from the everyday surface of the sun, it gets hotter. And how is that?
It all starts at the sun's core, where every second, nearly 700 million tons of the universe's most common element, hydrogen, are converted into helium through nuclear fusion, giving off the energy that becomes photons, otherwise known as light.
The sun's core is really hot, several tens of millions of degrees. And there, the temperatures are so high that protons, hydrogen nuclei, can come together, grab each other, fuse, eventually into helium, and in this way, release energy.
What happens with these photons, they go through this process, what we call a random walk, where they have to go through the layer of the sun, they get absorbed and then reabsorbed into lots of different photons at lower energy level. So this process of being absorbed and reabsorbed millions of times can take 150,000 years.
Once out of the sun's interior, photons are only 8 minutes away from Earth, but they're leaving behind a world in constant motion. The solar surface boils. Energy rises constantly from below. Coils of plasma and energy, called coronal loops, spring across the sun. While dark regions known as sunspots stretch thousands of miles, and at only 7,000 degrees Fahrenheit, these sunspots are the coolest part of the sun, emitting less light than the surrounding area.
If you were to pluck a sunspot away from the sun and place it in the sky, it would actually be as bright as the full moon.
Sunspots appear on the surface and are easy to see. Their genesis, however, is tied to the sun's deep interior and complex rotation.
The sun doesn't rotate like a solid body. Instead, it rotates more quickly near the equator than near the poles, which leads to sunspots. The equator completes one rotation in 25 days. Mid-latitudes complete one rotation in about 30 days, and near the poles, one rotation is completed in about 35 days.
Called differential rotation, this process makes the sun's interior churn at different speeds, creating intense magnetism in the form of millions of magnetic field lines, which get mixed up as the sun's interior twists up like a rubber band.
This builds up pressure, which makes them buoyant. So they float to the surface, and where they pop through the surface, they create sunspots.
Once on the surface, the now twisted and balled up magnetic field lines block the convection of superhot plasma from rising, making sunspots appear dark.
And when those sunspots start to twist around, you can imagine that you have one sunspot here and one sunspot here, and there's a magnetic field that connects the two. And that magnetic field gets twisted, and eventually, the same sort of thing that happens with a rubber band, it pops. And when the magnetic field pops, it releases energy. And in the case of the sun and solar flares, it releases huge, huge amounts of energy.
The magnetic field lines created by the twisting and churning of sunspots, though invisible, can be seen in the dramatic formations on the surface of the sun, in the form of flares and prominences. It is here that the sun's influence starts, as the breaking of these magnetic field lines drives massive amounts of energy from our nearest star out into the solar system. And it is these magnetic field lines that are behind most theories on why the corona is so much hotter than the surface.
It's pretty clear that it has something to do with the magnetic field that heats the corona. But presumably there are waves along the magnetic field that bring energy from underneath the surface of the sun into the corona.
The solar probe Hinode, which means sunrise in Japanese, was launched in 2006. Its mission to study the interaction between magnetic field lines and the corona. Recently, it captured images of one of the waves thought responsible for heating this enigmatic region, Alfvén waves.
Alfvén waves are waves that occur in a plasma, in a bunch of ionized gas, threaded by a magnetic field. And indeed, it's thought that these Alfvén waves might be bringing turbulent energy from inside the sun out to the corona, where that energy heats the corona.
Energetic Alfvén waves form inside the sun and travel up through the surface, making the looping magnetic field lines sway and vibrate.
And so through this vibration or this oscillation, they're having friction with the magnetized plasma surrounding it in the corona. And through this friction, the heating occurs.
It's this heat, delivered to the corona, that radiates out into space, filling our solar system with the sun's energy. But this energy is not constant. Our sun is an ephemeral body, never the same from one day or 1 year to the next. Like Earth changes with seasons, so does the sun. And when the solar seasons change, anything can happen. Day in and day out, the sun we see appears the same. But like Earth, the sun has seasons, solar minimum and solar maximum. Two distinct personalities that can affect our technology and possibly even our weather. The transition between solar minimums is called the solar cycle, an average 11-year period in which the sun's activity maxes out, then ebbs again.
The primary measure of the solar activity cycle is the number of sunspots visible on the sun.
During solar minimum, the period with the fewest sunspots, solar activity is limited. When sunspots break through the surface during solar max, the sun's power reaches out.
When there are lots of sunspots, there are lots of flares, and coronal mass ejections.
Increases in solar activity enhance the connection between Sun and Earth. Energy expelled from the Sun can create disturbances in the near-Earth environment.
The Earth is embedded in the solar atmosphere, and so what happens on the Sun affects the Earth, and that's what we call space weather.
Accurate space weather forecasting is the ultimate goal, but this can be hard. The Sun is turbulent, especially during solar maximum, the peak of solar storm activity.
During solar maximum, the magnetic field of the corona becomes very complicated, and you have magnetic field everywhere, all around, even near the poles. You can have coronal mass ejections and flares and solar storms occurring sometimes several times a day.
Solar flares, violent eruptions of energy, usually near sunspots, burst into space. Like a bolt of lightning, quick and powerful, they can happen over a matter of minutes and can give off the same amount of energy as 1 billion megatons of dynamite.
Solar flares are gigantic outbursts of energy from the Sun, coming from a very small localized region of the Sun's surface. So they're very concentrated ejections of energy that heat the surrounding gas to 10 million degrees.
Solar flare is sort of like a snapping of the whip. It really releases a lot of energy very quickly, accelerating particles almost up to the speed of light.
The particles from the very most energetic solar flares can reach us in something like 15 minutes.
But the solar hurricane of space weather comes from coronal mass ejections. These massive blasts carry billions of tons of superheated gas and plasma into interstellar space.
So coronal mass ejection is where a huge amount of mass and energy is expelled away from the solar surface. So if you can imagine this huge amount of mass and energy traveling away from the Sun at these large speeds, sometimes at over 1 million miles an hour.
They throw these like big bubbles of hot gas and magnetic field. It can move off the Sun so quickly that it actually creates a shock wave. They're the biggest storms, and they're the important ones for understanding space weather.
Solar probes, like SOHO, have captured the Sun expelling massive amounts of energy into space. But scientists are most concerned when they see something called the halo effect, when the cloud of energy appears to surround the coronagraph. That means the Sun has aimed its latest blast at us, like in the massive solar storms of 2003.
The fastest coronal mass ejection ever studied in modern times came from these storms.
Shortly after the initial blast from the Sun, SOHO was bombarded by charged solar particles, protons and electrons, overwhelming the camera and causing the image to drop out.
What happens is you see a sort of snow on the camera, all sorts of sparkles going by, and that's the particles accelerated by the coronal mass ejection hitting the actual camera on SOHO.
If caught off guard, solar storms can harm astronauts, exposing them to the same amount of radiation in seconds that we receive on Earth in a year.
So if we're going to send astronauts back to the Moon and to Mars, it becomes very important to be able to determine when these coronal mass ejections and storms are going to occur. The charged particles embedded in these coronal mass ejections are dangerous. It's a lot of radiation that would hit an astronaut.
Astronauts and satellites aren't the only potential victims of solar storms. The particles blasted towards Earth can interact with our magnetic field, occasionally wreaking havoc.
When this material comes smashing into the Earth's magnetic field, it causes it to ring almost like a bell. And when you have a magnetic field, and when that magnetic field moves, physics tells us it's going to create currents. And so electrical currents will be created in the outer atmosphere of the Earth. And these electrical currents can cause all sorts of disturbances.
The currents create problems for satellites orbiting the Earth. They disrupt global positioning systems. They can interfere with communications equipment, causing radio blackouts and knocking out mobile phone systems.
These mass ejections can send so many charged particles toward the Earth that some of them make it through the Earth's magnetic field and even reach power stations here on Earth, causing surges of electrons and power outages and short circuits and things like that.
In extreme situations, solar storms cause excessive radio interference and increased levels of radiation, requiring planes flying near the poles to be rerouted. But as powerful as the storms were in 2003, they're no match for what astronomer Richard Carrington saw in 1859, a super flare.
The super flare of 1859 was incredible because prior to this event, we didn't even know that flares existed. Carrington saw this huge bright flash on the sun with an unaided eye, and in order for him to see that, it had to have been a super huge flare.
There were reports of telegraph lines running without being powered.
We probably won't see another one that intense in our lifetime, although it's hard to say for sure. The sun has thrown us some surprises.
If a similar storm were to strike today, one recent estimate projects 130 million people would lose power, possibly for months.
Most of the electrical infrastructure, the power grids around the world would be knocked out. A lot of the transformers would be overloaded. Having a large portion of the population with no power for many months could cost huge amounts of money. People have estimated that it would be upwards of $2 trillion.
We won't know unless it actually happens, and the more warning we get, the more we can do to reduce the economic impact, which is one of the reasons why we're studying the sun.
Scientists are a step closer to being able to predict these storms since the launch of the Solar Terrestrial Relations Observatory, also known as STEREO. This pair of probes now gives scientists the ability to see the sun in 3D.
So now, when one of these coronal mass ejections travels towards us, we're actually looking at the side view. And so we can see how fast they're traveling, we can see how they're evolving, the structure.
In 2011, the STEREO probes will reach their ideal vantage point, opposite sides of the sun, giving NASA a 360-degree view, allowing them to see what is coming from the far side of the sun before it impacts Earth.
And so for the first time, we're going to have a complete view of the sun all the way around. So this is going to allow us to see everything that's happening on the sun at the same time, and this will lead us again into a better ability to predict these types of storms.
But as dangerous as solar maximum can be for its increase in space weather, the sun's solar cycle counterpart and calmer period, solar minimum, may come with its own dangers.
When there are a low number of sunspots on the sun, the climate here on Earth can actually cool a little bit.
2008 saw the fewest number of sunspots in nearly a century, with a total of 266 sunspot-free days.
In 2008, we were at sunspot minimum, but by now we expected to be climbing out of that sunspot minimum, and we're not. So this could mean that this particular sunspot minimum is more protracted.
Scientists believe that past protracted minimums have had a chilling impact here on Earth.
Now, every once in a while, the sunspot activity cycle seems to just go away or become much diminished. There was such a period around 1650 to the early 1700s.
There were only about 50 sunspots recorded, when normally in the same time frame there are tens of thousands. So it was a really low period of sunspots.
It was called the Maunder minimum. The sun was in a quiet state. And that was associated with lower than normal temperatures here on Earth. Europe experienced sort of a mini ice age during those few decades.
Whether or not this current minimum will be protracted enough to have such a large impact on Earth won't be known for years. But another measure of solar activity, the solar wind, appears to be waning. And that could impact Earth tomorrow. Bathed in the sun's atmosphere, Earth is shielded from deadly cosmic rays. And while the sun's power protects us, it can also harm us. Life on Earth survives this close to its star, thanks in part to its ozone layer. But what would happen if the ozone layer were gone?
If Earth lost much of its ozone layer, ultraviolet radiation from the sun would penetrate through the atmosphere and reach the Earth's surface.
The sun's massive amounts of ultraviolet rays would quickly eliminate most basic elements of the food chain, wiping out plants and then animals.
If we are bathed in huge amounts of ultraviolet light, eventually the life on the Earth would die.
But what could cause such a catastrophic collapse of the ozone layer? Something the sun is supposed to protect us from: a gamma ray burst.
Gamma ray bursts are intense, brief, flashes of the most energetic kind of radiation known, gamma rays.
The most powerful events in the universe. In seconds, they give off the same amount of energy that the sun will emit in its entire life. They occur when certain large mass stars die or even collide.
They can be generated from very extreme processes, such as large mass stars collapsing into black holes.
They occur somewhere in the sky roughly once per day, and they come from very, very far away. Most of them are billions of light years away.
But just 8,000 light years away, deep within the Sagittarius constellation, buried in a pinwheel-like formation, looms a potentially ticking time bomb. WR-104. 2 stars locked in a cosmic dance, spinning a full rotation once every 8 months. But one of these stars is on the verge of going supernova and emitting a gamma ray burst.
Now, one of these 2 stars is a very massive star that might someday form a gamma ray burst, and its beam might hit the Earth. If the high-energy beam from a gamma ray burst were pointing directly at the Earth, it could spell real danger.
The radiation from the gamma ray burst would be so intense, very short, on the order of 10, 20 seconds, but this would set up a chain of events which eventually would deplete the Earth of maybe 50 or more % of the ozone layer.
Scientists have speculated that a nearby gamma ray burst caused an ancient extinction on Earth millions of years ago.
At the time, there was only sea life that existed, and even though the sea life deep beneath the sea wouldn't be directly affected by the UV radiation, the plankton and the life on near the surface would die off, and therefore the food chain would be affected.
The threat is heightened even further by something scientists have witnessed over the past few decades: a 20% decrease in the power of the sun's solar winds.
The solar wind is the steady emission of particles from the sun.
They carry the magnetic field that is in the solar corona out into space.
It exists even when there are no coronal mass ejections or solar flares.
The solar wind continues way out beyond the orbit of Pluto and has actually blown a bubble in interstellar space.
Now, that's a bit of a protective bubble because the magnetic fields protect us from charged particles coming from outside.
Normally, solar winds stream off the sun in all directions at speeds of 1 million miles per hour. Pulling the sun's invisible magnetic field along with it, they form the solar system's defense against intergalactic intrusion, the heliosphere.
The heliosphere is the very boundary where the solar wind hits intergalactic space. So it's this shell that's surrounding the sun and the solar system where it protects us from intergalactic winds here on Earth.
Recently, scientists have learned that the heliosphere is shrinking and getting weaker.
The solar wind pressure has been measured to be decreasing over the last 25 years. In fact, the heliosphere, where the solar wind pressure is extending out to, has actually shrunk a bit.
A weaker heliosphere increases the possibility that Earth will be exposed to harm from intergalactic cosmic materials.
So if there's less solar wind, then the heliosphere itself is going to shrink. And that makes it easier for more cosmic rays to enter into the solar system.
Already, the amount of high-energy electrons, a small but telling aspect of cosmic rays around Earth, has jumped in number by 20%.
Looks like the cosmic ray electrons have increased, and you would expect that. If the solar wind has decreased by 20–30% over the last 15 years, the bubble will have gotten smaller, and you expect an increase in galactic cosmic rays.
The good thing for us is that we live on a planet with a thick atmosphere and a magnetic field. So we have 2 types of shields that protect us.
But that could change when WR-104 emits its gamma ray burst, possibly upsetting the balance of Sun and Earth, a balance that may already be in jeopardy because of something the Sun did billions of years ago. Over billions of years, the Sun and the Earth have developed the perfect balance for life to thrive. Sitting in the Goldilocks position of the solar system, not too hot and not too cold. The sun gives us just enough light, just enough heat, and just enough energy to fuel our planet and our lives.
The sun drives everything on the Earth. The sun is the energy source of the Earth. So all of the energy that's given off by the sun heats up the Earth. This drives weather. On a larger time scale, this drives climate. So basically the sun is the energy source. It's the battery that drives the whole Earth environment.
Plants harness the sun's energy through photosynthesis, creating carbohydrates. People and animals consume these carbohydrates, converting them into energy we can use. Even the fossil fuels that power our lives were created by the sun. But our increased use of fossil fuels seems to be upsetting the balance between the sun and the Earth.
Since all living material gets its energy initially from the sun is the source of the fossil fuels, whether it's trees, whether it's other things that have been trapped in the rock layer and then squeezed and slowly over millions of years made into the hydrocarbons that we know them as. And we then harvest and use those from underground.
The fossil fuels that we burn today unleash the sun's energy from millions of years ago, overwhelming the balance struck between our planet and its nearest star.
If we burn all this, we will have changed the atmosphere unrecognizably long before we get to a point when we're actually running out of the resource itself.
Already we have seen the effects of too much solar energy in the rise of global temperatures. The release of millions of tons of ancient solar energy stored in fossil fuels has amplified the necessary and natural process called the greenhouse effect.
Many people think that the greenhouse effect is a bad thing. Well, in fact, it's not. It keeps the Earth warm. Without the greenhouse effect, Earth's oceans would be frozen solid. What is bad is too much of a greenhouse effect. If there's too much carbon dioxide and water vapor and methane in the Earth's atmosphere, then those gases trap too much of the sun's radiation, elevating Earth's average temperature, leading to global warming. Now that can cause a melting of the polar caps and a rise in the ocean levels, leading to just a calamity on Earth if it happens too quickly.
Not only will our atmosphere continue to trap more heat, it could start to decay. Continued use of fossilized solar energy will allow in undesirable amounts of radiation from our sun. Right now, our ozone layer prevents the majority of the sun's ultraviolet radiation from reaching Earth, while allowing just enough sunlight to give us what we need to survive.
Sunlight interacting with our skin produces vitamin D, which is a very useful vitamin.
Vitamin D can protect us from a number of diseases, including the bone disorder osteoporosis and heart disease. But here, too, a balance has been struck. Too much sun can alter our DNA, causing skin cancer. Maintaining the equilibrium between sun and Earth that allows life to thrive will require using less of the sun's ancient energy and more of the energy it delivers on a daily basis. After all, the sun's energy output is estimated to be 386 billion megawatts. Meaning in 15 minutes, our star radiates as much energy as all life on Earth consumes in 1 year. Tapping this power source has been the goal of scientists for decades.
For sheer size, a solar satellite would be unprecedented. A structure 35 to 40 square miles covered with solar cells, able to capture the sun's energy 24 hours a day and beam it to Earth.
NASA has yet to achieve a goal on that scale, but their work with solar technologies in space has advanced technology here on Earth.
History of solar cells is essentially a technology that came back down to Earth from space. When we first started to work on the Apollo and Mercury and Gemini programs, we needed power plants in space. Solar cells were a natural way to do that.
Currently, we have two ways of directly harnessing the sun's energy. Solar thermal, which converts the sun's energy into heat by concentrating it enough to drive turbines, and solar panels, which use silicon-based technology to directly convert the energy from above into electricity. We can indirectly tap into the sun's power through wind turbines, capturing the energy produced by the weather the sun helps create. These technologies are constantly being improved. But some of the most interesting new science is coming from a very old process, photosynthesis.
There's some really exciting opportunities as we move from the world of semiconductor solar cells to organic ones.
Attempting to mimic Mother Nature, scientists have been able to create electricity from something found at the farmer's market, spinach.
There's organic molecules in spinach, in all green plants, but spinach happens to have a very convenient one, where you can harvest that peptide, that molecule.
Researchers were then able to put that peptide into a kind of solar sandwich, placing it between two electrically conductive materials.
And when it's exposed to sunlight, it will circulate electrons, which is current, which is electricity. So these organic molecules can actually become little solar cells.
In order to maintain the balance between Earth and our nearest star, it's become clear we must focus on finding ways to fuel our lives with the energy the sun supplies today. After all, the promise of solar energy is that for as long as the sun shines, its power can be ours. But what will happen when its power becomes too plentiful? The elements that make up the sun, the earth, and even humankind all come from one place: stardust, the remains of stars that lived billions of years ago. And just as those stars died, so too will our sun.
In about 5 billion years, the sun will pretty rapidly become much more powerful, much brighter, and much bigger.
The sun will reach a stage where it has burned through all of its hydrogen. And once that happens, it will start to burn through all of its helium.
The sun will start to expand as it reaches a stage called a red giant. As it expands, it will start to expand into much larger size and fill the inner solar system.
The orbits of the planets themselves will actually expand outward as well, because it's not as massive.
During that stage, some instabilities, which I call cosmic burps, will cause the sun's outer atmosphere to be gently ejected.
The outer layers of the red giant will just keep drifting off at some slow rate.
The hot inner layers of the sun will ionize that cloud of gas surrounding it and cause it to glow. So our sun will be surrounded by these glowing clouds of gas.
They will form what's called a planetary nebulae. They're beautiful shapes. Some are just purely round, but some have been distorted into other shapes. They've come off non-symmetrically from the star underneath.
What'll remain is the contracting core of our sun. And it won't produce any new energy through nuclear reactions, because all the nuclear reactions will have stopped. So it'll continue contracting and slowly fading with time.
It's very similar to the process that creates, say, supernova, but our sun is not big enough, doesn't have enough stuff to actually create a supernova. So its final stage will be this object we call a white dwarf star.
What remains is this little, relatively small white dwarf star, and it is a very quiet, what we call happily retired star.
It'll be about the size of the Earth, it won't get any smaller, and it'll sit around as this very highly compressed rock forever. It'll just liberate its energy, growing ever colder and dimmer with time, until finally it just fades from view.
The death of the sun will have catastrophic effects on the solar system. If the massive expansion doesn't swallow the nearby planets, it will likely change their orbits and superheat them, including Earth.
Earth's surface will be fried to a crisp.
The Earth is probably going to get baked one way or the other.
I mean, imagine the sun being 100 or 200 times brighter than it is right now. Imagine how much the Earth would be heated. It would not be a pleasant place to be.
It actually may get baked before the sun completely dies, because the sun will get hotter even before it becomes a red giant and gets as large as the orbit of the Earth. It'll get warmer, and at some point the Earth will get hot enough so that water will boil.
So the oceans will evaporate away, and all of life as we know it will cease to exist.
If there's anything left of the Earth, the sun will shrink down to a white dwarf, and the Earth will, instead of heating, freeze.
This will not be a pleasant place to live.
But that's billions and billions of years from now. We've only had rockets in space, satellites, for 50 years or so. Now we're talking billions. So clearly we'll be able to travel around the solar system at the very least, to go to places that will be at the temperature that the Earth is now, and we'll be able, by that time, to go to more distant solar systems. So I don't spend a lot of time worrying about what's going to happen to the sun in 5 billion years.
The sun gave us our life, and it will eventually take it away. And though the Earth will die, it and everything on it will in some part live on. The stardust that gave Earth and all of its inhabitants life will one day be